Do I have audio? Yes, I have audio. Excellent. All right. Pass this around so y'all can start signing in. We are going to finish up the work energy principle today. We've been talking about work done by a constant force, which you would think means that's causing a body to accelerate. But in fact, it does not. You have no net acceleration when you are moving an object at a constant speed. And it turns out that you're doing work against another force. The example we were talking about was pushing a box across the floor. And what you're doing is you're pushing a box and by applying a constant force, moving the box from point A to point B at a constant velocity, meaning that it's unaccelerated, its speed is not changing, but you're still having to exert a constant force to keep it moving because you are exerting a force that is exactly equal and opposite to the force of friction pushing against you. Both you and the force of friction are non-conservative forces. All right? You are a non-conservative force because you're an external force. You're not part of the energy of the system that already exists. The friction is a non-conservative force because it is converting energy into heat and dissipating it into the atmosphere. Okay? You'll recall, energy cannot be destroyed, it cannot be created, it can only be converted or stored. So you, as a non-conservative external force, are converting chemical energy into physical work by applying a force in opposition to the force of friction, causing the box to move across the floor. The friction is applying an equal and opposite force, and it's all being turned into heat that's radiating out into the atmosphere. And at the end of the exercise, literally exercise, the box has been moved a certain distance. Here, pass this back. Okay, there you go. Now, what if you applied a greater force than the force due to friction? What if you wanted to get it done faster? Now, when you initially start this motion, this box moving, you're going to give it some initial velocity that you're going to move it at. Now, whatever that velocity is, that is going to be accomplished by doing a very small amount of work over a very short distance, right here at the beginning. But once you've achieved that velocity, you're not going to keep pushing it with that same force. You're going to push it with a lower force, with a constant force, just enough to keep it moving at that initial velocity. That's what's going on. Now, we generally oversimplify it by ignoring that initial little bit of work you do because it's a small amount of work over a very short distance, and so we ignore it. But that's what happens. That's where that initial velocity comes from. But what if you wanted to move it faster? You wanted to get done quicker. So you keep pushing harder and harder and you accelerate that box. You apply a force to that box, even if it's a constant force. If it's greater than the force of friction opposing you, then the net force on the box is going to be some positive force that you're applying, and it is going to accelerate. Okay? And so it will no longer be moving at a constant speed. It means you're going to be moving faster and faster until you get to where you're going. At that point, you immediately stop applying a force. Now, the work you have done is over. Whatever work you did, it's been done, and at that instant, the box still has that kinetic energy, that velocity that you have imparted to it. Now, there's still a force of friction acting against it, so it's very quickly going to decelerate back to rest. But at that moment that you stopped doing work, at the moment your work was finished, was over, the box had a velocity. It had some kinetic energy. And that's the point that I'm getting to here, is that when you sum all of the work done by non-conservative forces, you will see that that results in a change in the kinetic energy of the box. Okay? And there is a principle here. This is the work energy principle. The total work done on an object is equal to the change in energy. Okay? Now, you've been accelerating this box for some distance. And if you will go back to your handy-dandy kinematic equations, what do we have? V squared equals, let me write this down up here. One of the kinematic equations. V squared is equal to V naught squared plus 2 times the acceleration times delta x, change in position. Yeah. So, if we solve this equation for A, we end up with A equals V squared, V final squared minus V initial squared divided by 2 delta x, or 2 times the distance it's moved. All right? Is this familiar with everyone? Well, we also know that the net work done is equal to the net force times the distance that it was moved. And the net force is, well, we can just rewrite that now. The net force is a mass times the acceleration times distance. We substitute this for our acceleration, and we get net work is equal to mass times V squared minus V initial squared divided by 2 times the distance it traveled, and then multiplied by D. Well, the D's cancel, and we have the net work is equal to mass divided by 2 times V final squared minus V initial squared, or mv final squared over 2 minus mv initial squared over 2. Is any of this looking familiar? We define this term as the kinetic energy. Now in the book it's going to be specific and say the translational kinetic energy, meaning the translational means linear motion across in space. And don't let it confuse you when you run into it. When you see translational kinetic energy, just understand they're only talking about as compared to rotational kinetic energy, which we'll get to in, I think, chapter 8. Okay, so don't let them throwing in that extra word translational confuse you. We're still talking about kinetic energy. And when we define the kinetic energy as being equal to 1/2 mass times velocity squared, what we see here is that we've got the net work done on the object is equal to the final kinetic energy minus the initial kinetic energy, or the change in kinetic energy. Okay? This is for non-conservative forces acting on an object. Okay, now in this case, the forces involved are the force you apply to the box, which is a non-conservative force. It's an external force. Any external force, by definition, is not conservative. It's something that's being added to the system. Okay? The force of friction is not a conservative force. All right? It is a force that is going to constantly convert energy in the system and dissipate it out into the atmosphere as heat. Okay? It's converting energy from the system and transferring it out of the system. It's a non-conservative force. Think back to the beginning of the semester. What was the difference between distance and displacement? If the impact of a force, if it depends on the actual total distance traveled, then it's non-conservative. If it is only dependent upon the displacement, the starting and finishing point, the starting point and ending point, and the shortest distance between them, then it's a conservative force. U as an external force actually depends on the total distance that you push, not just where you start and stop. Okay? The force of friction is going to dissipate. The further you push it, the more it's going to dissipate. It's a non-conservative force. Now, they say here at the bottom of page 143, they say the net work done on an object is equal to the change in the object's kinetic energy. Well, that is technically a true statement for what based on what we've studied so far, but it is an incomplete statement. Okay? We're going to see here in just a little bit that this is true of non-conservative work done by non-conservative forces. Now, when we start talking about conservative forces, we're talking about forces that don't matter how far you travel. They don't depend on total distance. Total distance is irrelevant. What they depend on is net displacement. One such example is gravity. And you should have learned this in the lab yesterday, that the amount of work you did against gravity, pulling that cart up that height, didn't matter if you pulled that cart a whole meter up an inclined plane, or if you just pulled it up a half a meter straight up. You did the same amount of work in both cases. The work you did was equal to the force you applied times the change in height. All right? So if you apply, however much force you applied over that much change in height, that's how much work you did. Now, what was different? When you were pulling it up an inclined plane, you were exerting a much smaller force. But you were exerting it over a larger distance. Not displacement, distance. You exerted a smaller force over a longer distance and did the same amount of work as when you exerted a larger force over a shorter distance. Okay? But in both cases, you did the same amount of work, moving that cart up that inclined plane. As you did the same work dragging it a meter up an inclined plane as you would have done if you'd have just lifted it straight up that half meter. This is the whole point and principle behind what we call simple machines, the inclined plane being one of them. The lever is another. Pulley, block and tackle, these are other simple machines. Remember when we did the pulley problem in homework where the piano mover had the 2 pulleys instead of just one? Whereas if he'd only been using one pulley, he would have had to have applied the total force of lifting that piano directly above gravity. But by adding the second pulley, he divided the tension that of the piano pulling down equally between 2 pieces of rope. So the force applied to either one of them was only half of what it would have been if you were just using one pulley. You applied half the force to move the thing the same distance. What changed was the amount of rope you had to pull. So you had to apply that smaller force over twice as much distance to do the same amount of work. So you had to pull twice as much rope to move the piano the same height, but you didn't have to pull it near as hard. Same thing with the inclined plane. You apply a smaller force over a greater distance to do the same amount of work. This is the whole principle behind simple machines. Now, gravitational potential energy obviously is a conservative force. So when you do work against gravity, gravity is doing work against you. Now, the example in the book was a backpack, moving a backpack up a hill or up an inclined plane. Now, as long as you were applying that constant force equal to the weight of the backpack, it didn't matter. You weren't accelerating it. You were just moving it to a higher and higher position in the gravity field, and therefore increasing its gravitational potential energy. What was the kinetic energy of the object once you got to the top of the hill, of the backpack? Kinetic energy was 0. It was the same it was at the bottom. Okay, by climbing the hill with that backpack, you did not do any non-conservative work on that backpack. All you did was change its potential energy. And that's the point. Work done by non-conservative forces changes the kinetic energy of a system, of an object. Work done by conservative forces changes the potential energy. Let's see. Let's say, okay, we'll look here at the work done by an external force is the distance times the cosine of the angle. So if you're moving an object from here to here, doesn't matter if you move it straight up or at an incline. If you move it at an angle, theta, then it's going to be the force you applied times the cosine of that angle times the distance you move it up that ramp. If you lift it straight up, it's just going to be, the angle is 90 degrees, so the cosine of, I guess you would want to use the sine instead of cosine in this case, but, or they're defining this as 90 degrees and that as 0 degrees, but the point is that if you move it straight up, then you apply the full force, you move it a shorter distance, but you do the same amount of work. Is that what they're doing there? No, that's what they're doing. They're saying that straight up is 0 degrees. Because they're going to say straight down is minus, is 180 degrees. So cosine becomes minus. It would be the same if we were defining 0 degrees as horizontal, then this would just be, would be written as d times the sine of the angle. So it's sine of 90 degrees, it's plus 1. It's sine of 270 degrees, it's minus 1. They didn't ask me when they wrote the book. So, we swim in the water where we live. All right, anyway, the work done against gravity is the mass of the box. The force is mass times gravity, and the distance is the change in height. So, that's where we're going. Then they say that the work done by, that's the work done by you lifting it up that distance. The work done by gravity is exerting the same force over the same distance. Okay? But it's exerting its force in the opposite direction. So it becomes minus mass times gravity times that same height. Now, what's the total work done moving that box up that distance, h? The total work done on the box is 0. Okay? But the work done by you, the work done by you is equal to mgh. The work done by the gravity is also equal to the negative of that, minus mgh. So, what they're doing is they're working out a way to define the work done by gravity is equal to minus mgh. Which is equal to the negative of the change in potential energy. And that's all That's all they're getting at. The work done by the conservative force, the work done by gravity, is equal to the negative of the change in potential energy. What other kinds of, I don't want you to get the idea that gravity is the only conservative force. What other kind of conservative force, or what other kind of potential energy might exist in a system, in a closed system? The book offers the example of a spring. We just used one in our lab yesterday as an example of doing work against a variable force, where the total work you did, the greater the force increased as you stretched it farther. And so the work, you had to do that whole integral area under the curve of force times distance in order to calculate the work done. But the point is that when you push in that spring, or when you stretch that spring out from its equilibrium point, what are you doing? You're doing work on a closed system, but you're also storing energy in that closed system. Because if you let go of that spring, it's going to go back to its equilibrium point. If you've compressed it or if you've stretched it, it's going to go back to that equilibrium. So when you do work on a spring, you are doing work on a conservative internal force, and therefore changing the potential energy of the system. Okay? And there are think of a clock. And I know y'all, clocks are the app on a phone. They're digital, but once upon a time, clocks were strictly mechanical objects. And in order to keep them running, they had to store potential energy inside the mechanism in the form of a spring. That's why you had to wind clocks. Once you wound it up, that stored energy was then released in small, controlled, little incremental pulses that cause the hands to move around at a constant rate and therefore keep track of the passage of time. Now, did all of this to get to chapter 6.5. Oh, we've still got a half an hour. We're doing good. You made me nervous when you started packing up. On page 150, let's look at this work energy extended under the whole conservative versus non-conservative forces. They write that the net work done on an object is equal to the work done by conservative forces plus the work done by non-conservative forces. Makes sense? You've got conservative forces doing work, you've got non-conservative forces doing work. The total work done, the net work done, is the sum of the two. But if you go back to equation 6.4, let me see that. Where's that at? Here it is on page 143. They said that the net work done was also equal to the change in kinetic energy. Okay? Well, the work conservative forces plus the work by non-conservative forces is equal to the change in kinetic energy then we can say that the work done by conservative forces is equal to the change in kinetic energy minus the work done by non-conservative forces. And I wrote that backwards, didn't I? I did. Work by non-conservative is equal to the change in kinetic energy minus the work done by conservative forces. But we've already seen that the work done by a conservative force is equal to the negative of the what? The change in potential energy. So the work done by non-conservative forces is equal to the change in kinetic energy minus the negative of the change in potential energy, so plus the change in potential energy. Now that was a whole long way around of getting to this statement. Work done by non-conservative forces, by external forces, or just non-conservative in general, will equal the change in the kinetic energy plus the change in potential energy. Now, this is a kind of a huge deal. All right, this is, as I pointed out to you when we started this chapter, we're starting to look at the laws of physics in a whole new way now. We are, in order to better understand exactly what's happening, how it's happening, why it's happening, we're looking not just at how do things move, we're not looking at the complexities of what changes, of how things change. We're looking at what stays the same. You know? What doesn't change. And the bottom line is, if you don't have any external work done on a system, the total energy of that system does not change. In any closed system, with no external forces at work, the energy is constant, the potential energy and the kinetic energy. This is the lab we're going to do when y'all come back. We're going to look at how the potential energy of a cart converts into kinetic energy by letting it roll down a ramp and then measuring its speed along the bottom, on the bottom. You know, it starts off at rest here and accelerates to some speed. We're going to calculate the potential energy of the cart at the top of that hill, and then equate that to the kinetic energy it should have once it gets to the bottom. The kinetic energy is 1/2 mv squared, so we'll be able to calculate. This is what we're going to say. We're going to say the mgh is the change where h is the change in height, is going to be equal to 1/2 mv squared when it gets to the bottom, and then solve for v. And then what you're going to measure is you're going to have a beginning and an end point on that long track. You're going to start your stopwatch at this point and stop it at that point. Get the time it takes the car to travel that distance, Divide it by that distance to get your velocity and find out how close it was. This is going to give us a whole new way to analyze problems and situations and how to solve them. And not just in terms of building roller coasters and cars, but in terms of anything that involves physics. Whether you're dealing with biology in a nursing school program, or electronics or electricity in a, building circuits or power grids or whatever. You're going to have, this is always going to be true. Energy will always be conserved. So whatever energy you start off with in a system, and then whatever energy you add to it, that's going to be, it's all got to go somewhere, and that's pretty much what it's going to boil down to, is keeping track of where that energy goes. Where is it dissipated out of the system at? How is it added to the system? When is the system truly closed? Do any of you have any questions? Have y'all started looking at the homework for this chapter yet? Any of it look like it's going to be a problem? Yeah? Well, now's a good time to start asking. Okay. Well, then I've got one more reminder for you. I will be here probably till about 3 or 3:30 this afternoon, so if you've got any outstanding homework, now's the time to get it finished and turned in. This week's homework is not due until Monday when we come back. But this is how things are changing now. As we're coming up on the end of this semester. We only got a few weeks once we get back, and it's over. Once we get back, homework is due when we meet on Monday. If you turn it in on Wednesday or on Tuesday during lab, or it's late, and it goes into the late pile. And I will grade it when and if I get a chance. Now, when I do grade late work after spring break, when I'm grading late work, I will grade the most recent late work first. So if you turn in this week's homework on Tuesday when we get back, and you also turn in assignments from 2 or 3 weeks ago, then the most recent homework will get graded first. Okay? So the later the homework is that you turn in, the less likely it's going to be to get graded and count. Okay? Like I was telling Ash earlier, if you have labs that you need to make up, I will still work with you to get in here and get you set up so you can do any labs that you haven't done. But it's going to have to be done on an as available basis. So if you have any labs that you know that you need to do and you've got time to get in here and get them done today, I urge you to do so. Any questions? Well, you gave me some homework. I'm taking your word for it that it's all of it. Okay. Got 1, 2, 3, 4, and 5. I got 5 of them. All right, well, then I'm going to bid y'all adieu and say have a good spring break and productive, and I will see y'all when y'all get back. Okay, Pastor, you.
So I was here not yesterday, but the week before, and I missed the week before that. So 3 weeks ago, that lab.
I don't know, we'll have to look.
Okay. I can check and see which one that but I'm not sure.
Nope. Garrett snuck one in on me.
Yeah. You gotta take it before 12.
Thank you.
We did work yesterday, the level of work, right?
Yeah.
Or was that next? Okay, that's one that one of them that I need to do. And then it says I didn't do centripetal force, but I'm pretty sure that I was here for centripetal force.
Did you turn in your lab report?
Unless I'm getting week 9 and week 10 confused.
No, the centripetal force was the spinning machine.
Oh, that is the one I missed.
Yep. Okay.
Those are the two that I missed.
Yesterday's and centripetal force. Okay, well, both of them are going to involve, you're going to need to be here because we're going to have to set up equipment for you to do it. Now, do you want to do one or both of them today, or are you too busy and you're going to need to do it after we come back?
I can do them today.
Okay.
I know that I need to do them.
All right. Well, I have a class in here for the next hour from 8:30 to 9:30. Wait, no. That clock's still on not daylight savings time.
Come back?
Yeah, in an hour after the class is done.
It might be a little bit later.